Hello everyone. In this presentation, Khinchin theorem, a very important theorem in the spectral analysis of a signal. For better understanding of Wiener Khinchin theorem, one should have the prior knowledge about Fourier transform and auto and cross correlation functions. If we look into the basics, signal can be analyzed in two domains. One is the time domain, where we analyze the variation of a signal parameter with respect to time. And the second one is the frequency domain, where we analyze the variation of a signal parameter with respect to frequency, which is also called as a spectrum. Generally, time domain analysis can also be called as temporal characteristics. Frequency domain analysis can also be called as spatial characteristics. This presentation is mainly focused on frequency domain analysis. As we discussed, if we consider variation of a parameter with respect to frequency, we call it as a spectrum. Variation of a parameter means it can be a voltage or it can be a energy or it can be a power. Suppose if we look into the definition of energy spectrum, it is defined as variation of energy with respect to frequency. If we consider variation of a power with respect to frequency, we call it as a power spectrum. Wiener Khinchin theorem states that Fourier transform of autocorrelation function of a wide sense stationary random process gives the power spectrum of that process. Hopefully, in temporal characteristics of signal analysis, you have studied about auto and cross correlation. So, for that auto and cross correlation function, if we take Fourier transform, that gives the power spectrum or that gives about the spectral characteristics of a signal. Let us look into details. Power density spectrum. We are considering a signal x of t, which we are assuming as a wide sense stationary random process, and autocorrelation is given by Rxx of tau. Then the power spectral density Sxx of omega can be obtained by taking Fourier transform of autocorrelation. You can see the expressions written over here. If you take the Fourier transform of autocorrelation function, you will get the power spectrum. If you take inverse Fourier transform of power spectrum, you will get back the autocorrelation function. These two equations are said to be Wiener Khinchin relations or Wiener Khinchin theorem. Suppose if we look into cross power density spectrum, here we are considering two different signals x of t and y of t, which are jointly wide sense stationary. And if we take Rxy of tau is the cross correlation function, because we are taking two different signals, so it is called as a cross correlation function. So the power spectral density will also be called as cross power spectral density, denoted by Sxy of omega, which can be obtained by taking the Fourier transform of cross correlation. The expressions are wrote down here for your convenience. So this gives a good insight that for better understanding of Wiener Khinchin theorem, one should have the knowledge of what is meant by Fourier transform, what is meant by cross correlation, and what is meant by autocorrelation. There are two approaches to estimate the power spectrum. One is called the direct method, which is also called as periodogram method, and the second one is called indirect method, which is called correlogram method. Let us discuss in detail about this. Suppose If you have a signal in time domain which satisfies declared conditions according to Fourier transform, then you can take fast Fourier transform of the time domain signal where you will get the magnitude spectrum. If you take square of the magnitude spectrum, you will get power spectrum, because we all know that square of the amplitude will give the power. So this is the direct method where you are taking the signal, applying Fourier transform, calculating the magnitude function and taking the square, which gives the power spectrum. In case if the signal does not satisfy the declared conditions, then you cannot directly apply Fourier transform. In such a case, you have to go with the indirect method, which is called parallelogram method. What Wiener Khinchin theorem states. In such a case, if you take a time domain signal denoted as u of t, which does not satisfy the declared conditions, then you have to calculate the autocorrelation function for it. For that autocorrelation function, if you take Fourier transform, that gives the power spectrum. So this is the indirect method of estimating the power spectrum, which is also called as parallelogram method. You can see here, generally frequency analysis and time domain analysis are like two eyes. From time domain analysis, we will get some information, and from frequency domain analysis, which we will get some other information, which are very important for a signal analyst to know the characteristics of the signal. If you take the two birds shown here, one is budgerigar and the second one is zebra finch. Here I just shown you a small example about their voice. Every bird will have its own voice. So if you see that, you can see what is its time domain and what is its frequency domain representation. If you see the second bird, zebra finch, you can see how its voice looks in time domain and how its voice looks in frequency domain. Different birds will have different types of voices. Accordingly, their frequency spectrum will also vary. Clear? So this is very useful and very important for the many people who works with the birds, and many researchers works on the birds to know about its their peculiar characteristics. The very important concept, the very important slide of today's presentation is applications of Wiener Khinchin theorem. The Wiener Khinchin theorem is a very simple approach, what we have discussed just now. Okay, this Wiener Khinchin theorem is very useful for analyzing linear time invariant system. Secondly, it is mainly used in the frequency analysis of signals in various communication applications like radar, satellite communications, signal detection, filtering applications, mobile applications, etc. and etc. Let us take some time in discussing the applications of Wiener Khinchin theorem. Suppose if you take a radar, we transmit the signal at a certain frequency. After that signal transmitted over a period of time, it will come back. If the signal comes back, we have to understand that there is some obstacle so that the signal is reflected and it has returned back. Suppose there may be a chance that the signal may be returned due to some other reason, or we have received some different signal. So to confirm whether we received back the signal whatever we have transmitted, you have to analyze the frequency domain of the signal what we have received back. If the frequency of the transmitting signal and the received signal are same, then you can confirm that the signal what we received is what we transmitted, and there is some obstacle. And if the signal is not returned back, it ensures that there is no obstacle. If you have seen the Titanic's movie, in that movie, you all know that the ship will blast with the iceberg and the entire ship will collapse and many people die. If we have used radar, it transmits a signal and it will identify that iceberg and may have given proper directions for the person so that we might have avoid that Titanic ship damage. So, in satellite communications also, we use some frequency for uplink, that is for transmission from Earth station to satellite, and we use some other frequency for downlink, that is from satellite to Earth station. So, frequency analysis is very important in all parts of engineering. And in medical applications, you know EEG and ECG. So a person's health analysis is also depends upon the EEG and ECG signal. There is a standard form of EEG and ECG, and if it matches to the standard form, then there are no abnormalities. If it is not matching with the standard form, there may be some abnormalities with the person. And it is also used, that is spectral analysis is also used for data analysis in geophysics, oceanography, atmospheric science, astronomy, earthquakes. Everywhere, wherever there is a signal, there is a need of signal analysis for better understanding of the signal characteristics. The two signal analysis are time domain and frequency domain. And we have lot more applications in day-to-day life for signal analysis where this Wiener Khinchin theorem is widely used. Thank you.